So today we're going to finish up the notes on section 8.9 on those logarithmic word problems, and we're on page 33 in the notes. Again, the idea with these word problems is we're taking the formulas that we looked at earlier in the unit and just using logarithms to solve for the exponent. Last time we looked at percent increase and decrease. Now we're going to start by looking at doubling time and half-life problems. Remember that our doubling time formula is y equals a times 2 to the x, and our half-life formula is y equals a times 1/2 to the x. A is the starting amount, y is the ending amount, and x, remember, is not the time, but is the number of time periods. More with that in a little bit. In our first example on page 33, a population of kangaroos doubles in population every 7.8 years. Initially, there are 32 kangaroos. We want to know how long it takes to get to 100. I'm going to use my doubling formula, y equals a times 2 to the x. I know my starting amount is 32. I know my ending amount is 100. I don't know how long I'm waiting, and as a result, I don't know the number of time periods that I'm waiting. So I'm going to leave my power empty, and I'm going to get the equation 100 equals 32 times 2 raised to the x. To solve this equation, I'm going to divide both sides by 32 to get the exponential piece by itself. I think 100 divided by 32 does divide fairly nicely. So I'm going to write 2 raised to the x equals 3.125. You could also leave that as 100 over 32 if you'd like. Well, now I'm going to take my exponential equation and I'm going to rewrite it in log form. I'm going to say log base 2 of 3.125 equals x. Log base 2 of 3.125 equals x. Go to your calculator and use your change of base formula, and I'm going to say log of 3.125 divided by log 2, which should give me x is about 1.6439 or so. However, I'm not done. The power with doubling problems and half-life problems represents the number of time periods. So I know that I need to wait 1.6493 time periods for the population to get to 100 kangaroos. In this case, how long is the time period? It's 7.8 years. If I'm waiting 1.6439 time periods, I can multiply that by 7.8 to figure out the number of years that that's going to be. I'm going to go to the calculator, take the answer that I got, multiply by 7.8, and I'm going to get 12.822 years. With all of these problems, the power we get tells us not the time, but the number of time periods. Once you have your number of time periods, you multiply that by how long a time period is to get an answer that will give you a time. Let's take a look at the next example. We're looking at a radioactive isotope with a half-life of 12.5 days, and it's decaying. Initially, we have 10 milligrams of the sample. How long will it take for you to have only 1 milligram of the sample remaining? I'm going to go use my half-life formula. Y equals a times 1/2 raised to the x. I am starting with 10 milligrams, so I'll fill that in for a. I'm ending with 1 milligram. I'll fill that in for y. I don't know how long I'm waiting, so I can't figure out the number of time periods. So I'm just going to write the equation 1 times 10 times 1/2 raised to the x. I need to get the exponential part by itself, so I'm going to go and divide both sides by 10. 1 divided by 10 is 0.1 or 1/10. Doesn't really matter. I guess just for some variety, I'll use 1/10 over here. And you've got a half raised to the x equals 1/10. I also switched the sides. Now I'm going to convert this into log form. I'm going to say log base a half of 1/10 equals x. Log base 1/2 of 1/10 equals x. Go to the calculator and use your change of base formula. Log of 1/10 divided by the log of 1/2, which should give you x is about 3.322 time periods. Remember again, x is the number of time periods. We're told that a time period is 12.5 days, so I'm going to multiply the answer by 12.5. Go to the calculator, multiply your long decimal by 12.5, and we're going to figure out that it will take 41.524 days. 41.524 days. One last problem over here. Radioactive substance has a half-life of 300 years. How long will it take for the substance to decay to 20% of the initial amount? I realize there's a percent given, but it's still just going to be a half-life problem. Now, we were not told the starting amount. We can actually just make up a starting amount, and you'll see why this works as we work through the math. Let's say, to make things easy, we're starting with, how about 100 milligrams? If we're starting with 100 milligrams, and we're waiting until it decays to 20% of the initial amount, well, what's 20% of 100? 20. You're going to end with 20 milligrams. I just made up a starting amount. I figured out the ending amount based on that. And again, you're going to see in a minute why it doesn't matter what I started with. It will work out no matter what you use. If I use my formula, y equals a times a half raised to the x, I'm going to say 20 equals, nope, sorry, we know the a value. I'm going to say 20 equals 100 times 1/2 raised to the x. I'm going to divide both sides by 100. I'm going to get 2 over 10 or 1 over 5 or something like that. So 1/5 equals 1/2 raised to the x. If I chose to start with 200 milligrams, I would have ended with 40 milligrams, 200 here, 40 here. You'd still end up with the same equation over here. That's why it didn't matter what I started with, because after dividing, you'll still get the same equation. I think it'll be easier to work with if I switch sides over here. So I'm going to say a half raised to the x equals 1/5. Convert this into log form. Log base a half of 1/5 equals x. Go to your calculator so you can use the change base formula. Log of 1/5, close the parentheses, divided by log of 1/2. I'm getting an answer of x is about 2.322. Oh, you know what? Oh, never mind. No, I was going to say it was the same as the last problem, but it's not. And that's the number of time periods. Then I'm going to multiply this answer by how long a time period is. So multiply that by 300. And we're going to get 696.578 years. 496.578 years. Last thing that we need to take a look at are those compounded interest problems. In Part A, $9,000 is invested in an account that pays 3% annual interest, compounded continuously. How long will it take for you to have $10,000 in your account? Well, when I see compounded continuously, that means I need to use the formula A equals P e to the RT. I know my starting amount is 9,000. I know my ending amount is 10,000. So I'm going to say 10,000 equals 9,000 e to the 0.03, because that's my rate. I don't know the time. So I'm going to write it like that. I need to get the exponential piece by itself, so I'm going to divide both sides by 9,000. I'm going to get 10,000 over 9,000 equals e to the 0.03t. And I think I want to leave this as a fraction, but I could simplify 10,000 over 9,000 into just 10 over 9. I'm going to say e to the 0.03t equals 10 over 9. Convert this exponential equation into log form. So log base e of 10/9 equals the thing that was in the power. Log base e of 10/9 equals 0.03t. And hopefully you remember from last time that log base e just means the same thing as the natural log of 10/9. Go to your calculator and find the natural log of 10/9. Should give us about 0.105. It's approximately 0.03t. Divide both sides by 0.03. And we're going to get a time of 3.512 years. 3.512 years. Next, $6,000 is invested in an account, 4% annual interest, again compounded continuously, which tells me I'm using the PERT formula. How long will it take for your investment to triple? Well, if $6,000 is tripling, that means you're going to be left with 6,000 times 3, you're going to be left with 18,000. That's my final amount, 18,000. My starting amount is 6,000. E raised to the 0.04 times t. Divide both sides by 6,000. And you're going to get 3 equals e to the 0.04t. I think at this point the work's going to be very similar to the last problem, so see if you can go, rewrite this in log form, and solve. I'm getting about 27.465 years. About 27.465 years. Last one that we're going to look at. $4,000 is invested in an account that pays 5% annual interest, compounded quarterly. How long will it take for you to have $4,500 in your account? If it says compounded quarterly, we're going to use A equals P times 1 plus R over N raised to the N T, our formula for compounded interest for anything but continuously. I know my starting amount is 4,000. Ending amount is 4,500. My rate is 0.05, And quarterly means n, the number of times I do this in a year, is 4. So I'm going to fill in a 4 for both of those n's. I'm going to get 4,500 equals 4,000 times 1 plus 0.05 over 4 raised to the 4t. I want to simplify this a little bit. Let me figure out what 0.05 divided by 4 plus 1 is. That's giving me 1.0125. And then I'm going to go. I'm going to divide both sides by 4,000. It does divide nicely, so I guess I'll just use the terminating decimal here. Otherwise, I should really leave it as a fraction to make sure my final answer is as exact as possible. 1.125 equals 1.0125 to the 4t. I'm going to switch the sides around so I can use Mrs. Eburn's circle trick here. 1.0125 to the 4t equals 1.125. Rewrite it in log form, log base 1.0125 of 1.125 equals 4t. Go use your change of base formula, log of 1.125 divided by log of 1.0125, getting about 9.481. Divide, and we should get a final time of about 2.370 years. And that does it for this section. Make sure you check out Google Classroom or the website for the homework. And next time we're going to start our new unit.